Welcome back. So we're going to continue talking about linear combinations. So a linear combination of vectors, v1 through vn. So I have n vectors. What I'm going to do is I'm going to scale each one, c1, c2. So all these c's are scalars, they're constant values. Any combination of these with any scalars is called a linear combination. So to understand this, we want to know if B is a linear combination of V1 and V2. Meaning, are there some numbers, we'll call them X1 and X2, so that I go X1 times V1 plus X2 times V2 equals B. Well, this, I could rewrite it using my vectors V1 and V2. I could write them like this. I could then scale in my X1s and X2s and then add them together. And now notice, as a reminder, an equation is equal if and only if the components are equal. So now I have this equation, and this equation. Wait a second. That means I have three equations, a system of equations I'm trying to solve. How do we solve these systems of equations before? Hopefully you're thinking, we turn it into a matrix. Exactly, so we turn it into this matrix right here, and then we row reduce it. Pardon my squigglies. All right, so I want you to pause the video and row reduce that new matrix all the way. Go ahead. Now, if you did that, I could take row 1 times 2 and add to row 2, row 1 times 5 and add to row 3. And then after I'm here, I could have said, okay, I'm gonna take 1/9 of row 2, and then I multiply that by 16 and add down, and notice I get a row of all zeros. All right, that's a good sign. But what this more importantly means is I don't have a row that is all zeros and then a constant. If this value right here was anything besides 0, we would be in trouble. It means I couldn't do it. But in this particular situation, it actually means, because I can continue doing my row reduction to a row reduced echelon form, and I would end up with this final matrix. But what's this final matrix mean? Well, it means that X1 is 3 and X2 is 2. So interpreting this, knowing that information, we actually just solved our specific problem. So that means 3 times this first times our V1 plus 2 times our second vector gives us our third vector. This linear combination is the classic question of linear algebra. Is there a linear combination? And again, notice it ties into row reduction and solving a system of equations. So there is, in this case, a linear combination. All right. So in reality, if I gave you this matrix, again, this is the matrix we had, I'm asking a question of, I'm really turning into row. If you remember, that was V1 and V2. If you look at this column, it's all V1. Look at this column, it's all V2. And this is that vector B we're trying to solve for. So in reality, our matrix turned into a vector equation. So matrices are essentially using vector equations. All right, now to understand linear combinations a step more. So if I give you a vector equation with a bunch of variables, x1, x2, all the way up to xn, corresponding to each one pointing to the appropriate vector, equals some other vector b, the same solution of this vector equation is the same solution as the augmented matrix. So why don't we just use the augmented matrix? In fact, that's what we do. So if B can be generated by a linear combination, if only there exists a solution. In other words, if the matrix or the system is consistent. Hey, that's kind of an important thing. All right. Now, we have one more detail. This is something called a span. Now I changed it to red because it's really, really important. It's going to come back up. A span is a set of all the linear combinations of a set of vectors. So if you give me a set of vectors, I ask what are all the different values I can place in front of each one of those vectors, any real number, what are all the different vectors I can get? In other words, the span is everything that's possible to create. All the linear combinations. This notice is something that's really, really big. More often what we ask is something inside the span? That's a way of asking, is it a solution? Does it have a solution? And the span itself is a subset of all the vectors of Rn. So it's called the set that is generated or spanned by V1 through Vp. All right, I hope that helps. That's section 1.3. Please let me know if you have any questions. Good luck.